Hi everyone. Thank you for inviting me to speak at this fantastic conference. I'd like to talk about some work that I've done recently about topologically embedding spheres in knot traces. This is a talk about topological manifolds. Throughout this talk, X is going to be a compact topological four manifold. So the main question that we're interested in is an extremely general question. And it's the following. So given a class in the second homotopy group of X, when can this class be represented by a locally flat embedding of a two-sphere? So we're in the topological category, so locally flat is the sort of correct embedding notion. So it means that the two-sphere appears locally to be an R2 and R4. And up to some sort of local homeomorphism. And this question is extremely broad. So every class can be immersed generically, a topological immersion. And perhaps you could also consider that every class can be embedded as some genus of surface. So the question is sort of when can we get this genus down to zero? And the question's been studied for a long time. There's many results that probably don't have time to go into in this presentation, but I'd like to draw attention to the fact that the most impressive results come after the watershed of Freedman and Quinn. Freedman proving the disk embedding theorem, and then the subsequent topological developments from Quinn allow the use of high-dimensional manifold techniques to be applied to problems like this. So that's what this talk is going to be about. Okay, so what's our X? We're going to fix a type of X. So this is a type of X that's not been considered before for this question. So knot traces. So fix an integer n and fix a knot in S3. So a knot trace is I'm just going to take the four ball and glue a two handle to the four ball along the knot and with framing n. So this is a pretty simple type of manifold. You consider that attaching this handle is going to have as its boundary the effect of doing surgery on the knot, doing a Dane surgery. So that's the first thing to note, is that you're going to get the n-frame Dane surgery on this boundary. But actually, homotopically, this is a very simple manifold. A two-handle is at its core a two-disk. So I've attached a two-disk to a contractible manifold. So this is a sphere, essentially, up to homotopy. So here's sphere has first homotopy group trivial and second homotopy group Z. So here's the sort of schematic I'm thinking about. So here's going to be the knot on the boundary. So this is a D4. And here's the knot. And it's a schematic of the handle. And then the idea is that the handle has this core D2. And well, every knot is homotopically trivial in the ball, so we can generically immerse this null homotopy. So there's always some immersed sphere generating this pi2, and our question is, can we come up with some conditions that guarantee this can also be embedded? So this is related to something already in the literature called n-shake sliceness. So this is a term coined by Aquilot, I think, but the notion has been sort of studied in some guys for a long time. So knot is n-shake slice precisely if this generator can be embedded as a two-sphere, is what that means. So that's a different way of thinking about this problem that we're trying to solve. So maybe the first sort of thing you can think about is that if a knot is slice in the topological category or the smooth category, then it's n-shake slice in those respective categories for all n. And that's pretty easy to see, actually. So that's not good. So let me move my window. There it is. So there's the core of the two handle, and if it's slice, it's got also this slice disk on the interior there. and that glues up to make an embedded sphere. So that's the proof. It's pretty simple. So you can think of shake sliceness as some sort of approximation to being slice. And you wonder about the converse. How good an approximation is this? So it's been known for some time that it's possible to construct knots that are n-shaped slice but aren't slice. So it's not a total correspondence, but still an open question is it possible to construct a zero-shaped slice knot that is not slice? So I think that's an interesting open question, because it's very tantalizing. You feel like you should be able to maneuver this embedded sphere into such a position that you can see this disk, but that's an open question. In both categories, smooth and topological. Okay, so let me sort of state the embedding result we've achieved here. Okay, so here are the authors. Yes, that's a lot of authors. Feller, Miller, Nagel, Orson, Powell, Ray. And that's a mouthful, so let's cut it down to the pithy acronym FMNOPER. So the FMNOPER theorem is as follows. So we take an n, we take a k, we consider the trace, and we consider a generator. And it says that generator can be represented by a locally flatly embedded two-sphere with a certain condition on the fundamental group of the exterior of the two-sphere. So with an exterior with a abelian fundamental group. And that's if and only if three conditions. So condition one, the half invariant of the knot should vanish. Two, the H1 of the n surgery, so that's going to have an n-fold cyclic cover. And we look at the H1 of that cyclic cover, so that's what it means to take these twisted coefficients. And that should vanish. Okay, that doesn't look very friendly, but stare at that for a second. So if n is 0, that's talking about the zero surgery, and it's talking about the infinite cyclic cover. So actually, when n is 0, that's the Alexander module. So when n is 0, it's saying Alexander module vanishes, or equivalently, Alexander polynomial 1. When n is not 0, actually, there's a sort of pleasant recasting of this condition. So here's that recasting. And this is essentially a theorem, an old theorem of Fox and Goeritz, that this quantity is 0 if and only if I take all the nth roots of unity in the complex plane, I plug them into the Alexander polynomial, I take their product, and that thing is 1. So hopefully you'll agree that even though it looks a bit intense, this is a very easy to calculate condition. And finally, this is the third condition is about Levene-Tristram signatures. So I look at all the points on the unit circle that are roots of unity, nth roots of unity, and they should all give me 0 Levene-Tristram signature. So even if you don't know what these are, the takeaway is they're all calculable from the Seifert form. So they're all extremely calculable, easy to calculate. So the other thing to note is I want to talk a little bit about this abelian condition, which is strong. So you should think of this as a strong thing to be asking for. When you have one of these spheres, you might end up with any number of different exterior fundamental groups. So this is characterizing a particular class of two-sphere embedding. And it's somewhat an artifact of how we're proving this theorem. But it's a fairly natural condition. And it's sort of directly analogous to this famous theorem of Freedman and Quinn, which says that Alexander polynomial 1 knots, a knot has Alexander polynomial 1 if and only if it's topologically slice and the slice disk has abelian fundamental group exterior fundamental group. So it's exactly the same condition as in that Freedman-Quinn theorem. So this can be read as a kind of shake-slice version of that theorem. And so this was the work done by Monopper, and I wanted to slip in that actually we've done some subsequent work, and this first theorem can be thought of as an existence theorem, and the second one is a uniqueness theorem. So we can prove as well that any two spheres of that type are topologically ambiently isotopic. So I'm not going to talk about that any further in this lecture, but yeah, feel free to ask me about that later. Okay, so I'd like to give you some idea of how to prove this thing, but I'd first like to say that it's useful, and because these conditions are so easy to calculate, you can use it to construct stuff quite easily. So here are some sort of corollaries that we've used that theorem to construct. So first of all, this one compares the ideas of sliceness and n-shaped sliceness. So I've said before you can cook up a knot that's n-shaped slice for some n but isn't slice, but actually you can do much better. So with using this theorem, we can find infinite families of knots, all of which are non-slice, but they're actually all slice, they're all n-shaped slice infinitely many n. So the second corollary is a sort of divisibility theorem. So it says if m does not divide n, then essentially their shake sliceness is independent. So for most pairs of integers, you can cook up one that's shake slice for n and not shake slice for n. That's a sort of necessary assumption about division, because actually if you check the conditions in the previous slide, they're going to give you these sort of descend under divisibility. So that's the best we can hope for in that corollary. And then the final corollary is, well, the sort of hinting at the analogy to Alexander polynomial 1, and the main use of this theorem recently has been to construct exotic slice disks. So we have a similar theorem. So for every n greater than 0, there is an infinite family of knots that are topologically but not smoothly n-shaped slice. So that's perhaps the sort of theorem you might expect if this were the analogy to Alexander polynomial 1 theorem. Okay, so these are the corollaries, and feel free to ask me about how to prove these. I'm in the comments or the office hours. So now I want to discuss the proof. So it's going to be a bit rushed and it's going to get a bit technical, but I'm going to try and maintain a kind of through line so you can see the big picture. Okay, so fix n and k. So what I want to do is analyze what I get when I have an embedded 2-sphere. So I've got this embedded 2-sphere, and this abelian condition on the exterior could actually alternatively be phrased as the group is Z mod n. That's the abelianization of any embedded sphere representing the generator. So then I can take a tubular neighborhood. So actually it's a tough theorem of Freedman and Quinn that locally flat implies globally flat. So this tubular neighborhood does exist. And this thing is homeomorphic to a D2 bundle over S2 with Euler number n. So what I want to do is cut that thing out. And what I end up with is a cobordism from the boundary of the trace, so that's the surgery manifold, to the boundary of this disk bundle, so that's the lens space. And what's more, you can note it's got the homotopy type of lens space LM1, so that's just compute the homotopy groups, they're the same. So I want to turn my attention to this boardism. This is really what I study. I don't actually study embedding, I study this boardism. I try to construct the exterior, or I try to analyze the exterior. So I really want to talk about the constructive side, but here's the idea to actually calculate that these three conditions are met is to use this V, and this V can be used to calculate the ARF, the H1, and the Levene-Tristram signatures. But really I want to move on to talk about how do I prove the opposite direction. So suppose these three conditions are met, these three vanishings are met, how do I embed a two-sphere? Well, here's my plan. First of all, I'm going to build a candidate V. So I want to build a Bourdism from the surgery manifold to the lens space that is homotopic to the lens space. So that should better exist if I'm going to have any luck. And then what I'd like to do is glue the disk bundle on and then identify that I've actually got a knot trace up to homeomorphism. Okay, so those are the two steps. So for the first step, I want to build a Bourdism. So here's the lemma. So maybe the first thing to think about is that there's always a Bourdism between the end-frame surgery on the knot and the lens space because all three manifolds are Bourdon. But if I want to do the next steps, I've got to have more control. So the control I need is that I need this Bourdism to be stably framed. And I want to have everything together with maps to the lens space. So this is what that means. So there is a diagram like this. So the bottom is a cylinder in the lens space, and there are maps. These maps are degree 1, and they respect stable framings on everything inside. Right, and how do you prove something like this? It's sort of algebraic topology. This is a Bourdism calculation. So you calculate Bourdism groups using an Atiyah-Herzebruch spectral sequence, and you analyze obstructions. So maybe interesting to note that when n is even, there is an obstruction. We actually need the ARF invariant to vanish, which we've assumed, so that's okay. When n is odd, actually this thing always just exists. There's a stably framed Bourdism over the lens space from these two things. Okay, so it's going to proceed by improving this W to be the V that we need, because at the moment this W could be anything. Okay, so there it is. There's our friend W. So the next step is I want to do surgery. So this is a sort of the traditional approach to making F a homotopy equivalence. So the first thing to do is I'm going to do one surgeries on W, and I want to kill the kernel of the pi1 map. So this is going to have the effect of making F into an isomorphism on pi1, which is good because I want the top manifolds W to be a length space up to homotopy. So there's no obstruction to doing this. I can just embed generators, do surgery with the framing given, and I can do it. Okay, so then the next stage, the final stage, I just want to cut out enough two spheres to reduce pi2 to 0. And here's the rub. Can I do that? No. So the problem is, in general, there's an obstruction to doing things in the middle dimension. So we've got to analyze the obstruction and hopefully either see it 0 or make it 0. Okay, so what's the obstruction? So this is an assumption we've made. This is part of one of the three hypotheses. And actually you can use this to prove that the obstruction defines a well-defined obstruction class in Wall's surgery obstruction group. So this is the L group, the simple L group with Z mod n coefficients. So we'd like to know whether or not our obstruction is 0. So I'm not going to tell you what this group is, but what I'm going to tell you is it's isomorphic to something. So a difficult calculation over a number of years produces that for all n, there is an isomorphism like this. And what are these factors? So this Z actually is just the ordinary signature of W divided by 8. And what's this other guy? Is something called the multi-signature. So I won't say what that is either. But what I will say is we're going to have a way of forcing the signature to be 0. But actually the multi-signature, there's no way to force it. It's got to be 0 already. But luckily, this is the point of assuming that these Levene-Tristram signatures vanish. Is that we proved that the multi-signature is equal to these Levene-Tristram signatures n3s. So this is an assumption we've made that these guys vanish. So actually, that part of the obstruction is already 0. And now we want to kill this next part. So we'll just add copies of the E8 manifold of Freedman, possibly the reverse orientation, and that's going to knock out that signature component. So there is now no obstruction. We do 2 surgeries, we kill by 2, and now we get this V that we wanted, which is homotopy equivalent to the lens space. Okay, so we're almost done. So final stage. The idea was we're going to glue back in the disk bundle. So this is, remember, Euler number n bundle, this D2 bundle over S2. And our hope is that the trace of n surgery. Well, if it is the trace of n surgery, then inside that disk bundle is the S2, and that's an embedded S2, and that's going to be the correct embedded S2. So is there a homeomorphism? So luckily, this was answered by Steve Boyer in his thesis to some extent. So what Steve did was to classify simply connected 4 manifolds with boundary up to homeomorphisms. So given some homeomorphism already on the boundary, when can I extend it to the interior? And so this is a very big, deep classification theorem. So we have sort of a very small part. We take a very small part of it and we analyze, in our case, what it means. And when n is even, actually Steve's theorem says, yes, these are homeomorphic, nothing more to check. When n is odd, Boyer's theorem says these are homeomorphic if and only if the Kirby-Siebenmann invariant of X is 0. So I'm not going to tell you what that is, but it's some sort of obstruction to X being a smooth manifold. So it might just be a topological form manifold. Okay, so how are we going to force this thing? Well, we don't have to force it. So we can prove actually that the Kirby-Siebenmann invariant of this X we've constructed is equal to the alpha invariant of the knot. So this is I think it's a nice application of some fairly recent technology. So the tau invariant of Schneiderman-Teigner. And so I can get into that a little bit with the questions if people are interested. And we've assumed the alpha invariant is 0. So actually, we're done in both the even and odd cases. So maybe a fun thing to note is we needed the alpha invariant to vanish for n even to kickstart the whole process, but we didn't need it over here. And whereas we could kickstart the n odd process without any assumption, we now need the alpha invariant to vanish to finish off the proof. So actually, the alpha invariant crops up in different places for n odd and even, which is kind of fun. So thanks for coming and listening to the talk. There's a bunch of stuff still to talk about. We could dig into some of these lemmas. The corollaries are interesting. They're fun constructions. We could also talk about where else this can go. So different groups, not just Z mod n, are a possibility, although that's quite hard. And I would love to talk about how you prove uniqueness of this, which is something we've been working on. Yeah, and if anyone has some ideas for more applications of this, I would love to hear them and discuss them. So, or if anything was unclear, I'd love to, try and clarify things. So, thanks very much for your attention, and yeah, I'll see you in the other talks.